Hello everyone, welcome to Sai Tutorials Jamkandi. In our tutorials, 10th class Kannada medium, English medium, maths, science, English classes are available in regular classes as well as in online classes. So please do share the information and learn more, and please subscribe our channel. So dear students, in the previous session we have discussed some related concepts related your syllabus, that is second chapter physics, electrostatic potential and capacitance. So in today's session we are going to learn the next concept, some related concept to capacitance. Okay, in the previous session I have discussed about the capacitor and capacitance of the capacitor and how it will be denoted and what is the SI unit of the capacitance and everything. So in today's concept, let us learn about some of the applications related to capacitance, that is spherical. Okay, in today's class, let us learn about spherical capacitor. Okay, capacitance of an isolated spherical conductor. What will happen in this case? Okay, what is the capacitance of the capacitor? First one is spherical capacitor. Suppose see capacitance of the spherical conductor. Okay, now capacitance of the spherical conductor. Consider an isolated spherical conductor which is having the radius r in free space. Okay, uh, let us consider a spherical conductor. Okay, just a second. Let us consider a spherical conductor. Okay, let us consider an isolated spherical conductor which is having the radius. Okay, this is the point at origin having the radius r. Okay, having the radius r which is having the point charge q at the origin. At the origin. So now let us charge q be given to the sphere which is assumed to be concentrated at the center. I have shown you that at the center the charge is concentrated at the center of the sphere. Now potential at any point on the sphere, potential at any point on the surface of the sphere is given by. Now the potential, okay, at any surface of the sphere V is equal to 1 divided by 4 pi epsilon naught into Q divided by R. Am I not? Okay. This is the potential. Potential at any surface of the sphere. This is equation number 1. Now, if we know that capacitance of the capacitor is given by Q divided by potential. Am I not? This is the equation number 2. Now, therefore, capacitance of the isolated sphere will become Q into or Q divided by what is V in the first equation? 1 divided by 4 pi epsilon naught into Q divided by R, or it can also be written as Q into 4 pi epsilon naught into R whole divided by Q. So here one Q and this one Q will cancel. So what is the equation? C is equal to 4 pi epsilon naught into R. This is equation number 3. Okay. Now 1 by 4 pi epsilon naught. Okay, this C is directly proportional to the R. Okay, radius of the sphere. So this condition will tell you that larger the sphere, larger is its capacitance. See, I have told you larger the sphere. It all depends on the sphere. If larger the sphere, if larger the sphere, larger is its capacitance, because capacitance is directly proportional to the radius of that sphere, or capacitance and capacity, and smaller the sphere, smaller is the capacitance or the capacity. This is the expression for capacitance of the capacitor in case of spherical conductor. In case of spherical conductor. If you consider, this is about the spherical conductor, where epsilon, if you consider C is equal to 4 pi epsilon naught into R, okay, into R. If you consider if it is in the medium, which is also equal to 4 pi epsilon naught into epsilon R into R, okay. Permittivity of the medium between the outer sphere of the radius, if you consider the radius B, and the inner sphere of radius A. So this is about the spherical capacitor. So the next important application of the capacitance of the capacitor is applied to the parallel plate capacitor. Parallel plate capacitor. How the capacitance of the parallel plate capacitor will vary, let us discuss. Okay. Capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor. Suppose if you consider the, just a second, if you consider the two parallel plates. Okay, these are the two parallel plate capacitors. Okay, these are the two parallel plate capacitors. Let D be the distance between the two plates. Okay, the distance between the two plates will be D, small d. Now, two plates of the capacitor is having plate R is given to the positive charge. Suppose if you consider this is as R having the positive charge and this is having S having negative charge, which is equal to the negative charge. Now let plus sigma be the surface charge density related to the this plate R and minus sigma be the surface charge density for minus sigma be the surface charge density for this for the plate. Yes. Okay, electric field in between the plate is given like this. Okay, electric field E. Okay, now suppose electric field between the plates is given by sigma divided by epsilon naught. This is equation number 1. Okay. Suppose let us consider the two parallel plates having R and S. So these two plates are having the charges like R is having the positive plus Q charge and S is having the minus Q charge. Suppose these are separated by a distance D where R plate having the charge density that is plus sigma and S is having the charge density minus sigma. Now the electric field, okay, now the electric field between the plates is given by E is equal to sigma divided by epsilon naught. This is the equation number 1 where sigma naught is the epsilon naught where epsilon naught is the permittivity of free space because in this case the medium between the two plates is considered to be in a vacuum or air. So epsilon naught is a okay where epsilon naught is the permittivity of permittivity of free space. Okay. Here epsilon naught is a permittivity of free space because in this case the medium between the two plates is considered to be vacuum or air. But magnitude of the electric field is given by see the magnitude magnitude of the electric field. Please note this. Magnitude of the electric field is given by E is equal to dV divided by dr or V by d. This is equation number 2. Okay. The magnitude of the electric field is given by E is equal to dV divided by dr or V by d. So where V is a potential difference between the two plates of the capacitor, or this equation can be written as V is equal to ED. Am I not? Okay. V is equal to ED. What is E? Sigma divided by epsilon naught and D as it is. This is equation number 3. Okay. This is equation number 3. Now, the surface charge density. Now, the surface charge density sigma is equal to Q divided by A. Okay. This is equation number 4. Q divided by A. Therefore, capacitance of the capacitor is equal to Q by V. If you substitute all the values, it will become A divided by QD. Or we will write C is equal to epsilon naught into A, because here Q and Q will get cancelled. Therefore, this will become small d. This is the expression for capacitance of the parallel plate capacitor. See, the parallel plate capacitor, what are the phenomenon you can derive here? See, the capacitance of the parallel plate capacitor is directly proportional to the area. Okay, this is area, directly proportional to the area of the plates A, and inversely proportional to the distance of the separation, and therefore capacitance of the capacitor is independent of the charge on the capacitor. See, you can't see the charge here, because that's why the capacitance of the capacitor is independent of the charge on the capacitors. Let me revise you again. See, let us consider the capacitance of the parallel plate capacitor. If you want to derive the capacitance of a parallel plate capacitor, let us consider the two parallel plates, those named as R and S, where uh, R is having the positive Q charge and S is having the negative Q charge, where R is having the surface charge density plus sigma and S is having the surface charge density minus sigma. Those two plates are separated by the distance d. So then the electric field in case of surface charge density is written as E is equal to sigma divided by epsilon naught. This is the equation number 1. Now, where epsilon naught is the permittivity of free space. Okay, permittivity of free space, but the magnitude of electric field is given by E is equal to derivative of potential divided by derivative of the radius. This is equal to the magnitude is equal to the potential divided by the separation between the two plates, that is d. This is equation number 2. So if you if you recorrect the equation, then we will get the potential V is equal to E into d. So from equation 1, E value, what is the E value? What is the E value? E is equal to sigma divided by epsilon naught. So I have kept here sigma divided by epsilon naught into D, and the surface charge density will become sigma is equal to Q divided by A. This is equation number 4. And so if you keep these equations in capacitance of the parallel plate capacitor, that is Q divided by V. So Q into what is V? Sigma naught into A divided by QD. So here Q get cancelled. The capacitance of the parallel plate capacitor will become sigma naught into A divided by D. This is the equation. Now, where if you consider this in medium, okay, if we having the medium, so the C can become epsilon naught into epsilon r into a divided by d, where epsilon r is the relative permittivity of the medium between the two parallel plates of area a and separated by a distance small d. Okay, so if you go on substituting the further, this is enough for you. I think this is enough for your syllabus. So if the capacitance of the some simple capacitors, if you consider the spherical capacitor and parallel plate capacitor, if you substitute in cylindrical capacitor, what will happen? We will get the 2 pi epsilon naught into epsilon r into L. Okay, L, the length of the cylinder, where L is the length and divided by 2.303 into log base 10 into B by A is the, where B is the radius of the outer cylinder and A is the radius of the inner cylinder. But because of for your syllabus, the spherical capacitor and parallel plate capacitor are important. So this will be derived. So now, very important concept, that is effect of introducing a metal plate. Okay, introducing a metal plate. See, if a metal plate of a thickness T is held parallel in between the plates of the parallel plate capacitor, the electric field inside the metal will be zero. Work done in moving the unit charge from negative to positive plate is V is equal to E into D minus T, the distance between the plates. Okay, the distance between the plates effectively goes on decreases. Hence, the potential difference decreases and capacitance increases, since E is equal to Q divided by A into epsilon naught into, where potential difference V is equal to Q divided by A into epsilon naught into D minus T. See, let me derive the derivation. Okay. In the same case, suppose the two parallel plates these are the two parallel plates these are the two parallel plates. Suppose if I consider this is P and this is Q, which is having the positive charge, this is having the negative charge. The separation between the two parallel plates, okay, the separation between the two parallel plates is given by D. D. So capacitance of the parallel plate capacitor I have derived in the vacuum or between the plates of the capacitor. So now let us introduce a dielectric slab of thickness T. Now let us introduce a dielectric slab having the thickness T. Okay, dielectric slab having the thickness T between the plates of the capacitor. So where due to polarization, due to polarization of the electric charges, these charges will get separated like this. Okay. Now the electric field. Now the electric field will be denoted as E naught. Due to polarization, equal and opposite induced charges appear on the two faces of the dielectric slab. Let me show you in separate. This is the slab. The separation of the charges will take place due to the polarization. Okay. Due to the polarization which is having the thickness T, the electric field, that is E naught bar, will be like this. I mean like this electric field. Now, these induced charges gives rise to a induced electric field, that is EP, which is in a direction opposite to the applied field. Okay, EP will be the, see, EP will be like this. I mean, EP will be in this direction. These induced charges separated out. See, in the positive charge, negative charges are, so negative charges came near to the positive charge, and lot of positive charges in the dielectric slab will come near to the negative electric plate. These induced charges gives rise to a induced electric field EP, but this EP will be in the direction opposite to the electric field E naught, the reduced value of the electric field in the dielectric, that is E. That is E. Sorry. Okay. The induced electric field, the reduced value of the electric field in the dielectric will become, that is E naught, but this EP is opposite to the electric field. This exists in a region of thickness T. Okay, this is exist in the region of thickness T, and E naught field exists in a region of the thickness D minus T. Okay. See, E is equal to E naught minus EP exists in a region of thickness T, and E naught field exists in a region of thickness D minus T. So the potential difference between the two plates, now the potential difference between the two plates will be given by E naught into D minus T plus ET. So let us consider, this is equation number 1. Okay. See, the potential difference between the two plates of the capacitor due to the thickness of T for the electric field E, where potential difference between the two plates of the capacitor is V is equal to E naught into D minus T plus E into T, where now where E naught, okay, where E naught divided by E is equal to K, or E is equal to E naught divided by K. Is it? Is it right or wrong? Right. See, E naught divided by E, that is the previous electrical the previous electric field E naught divided by the reduced value, that is E is equal to K, proportionality constant K, or E becomes E naught divided by K. Now if you substitute these values in equation number 1, now the potential difference V will becomes E naught into D minus T plus E naught divided by K into T. See, what is the common here? E naught is common. Okay. So, remaining terms are D minus T plus T by K. T by K. So, if we know that, okay, we know that E naught is equal to sigma divided by epsilon naught, which is also equal to Q divided by A into epsilon naught. We have derived in the parallel plate capacitor, that is E is equal to Q divided by A into epsilon naught. Now this is having the charge density, surface charge density sigma is equal to Q by A. So now the equation becomes, if you substitute E naught value, then the potential becomes Q divided by A into epsilon naught, the remaining terms D minus T plus T by K. This is the potential difference. Now the capacitance of the capacitor will become C is equal to Q by V. This is equation. This is equation 3, I think. This is equation number 3. Now the capacitance of the capacitor, this is equation number 4, where V is equal to this thing. So if you substitute Q and V, what will be the answer? If C is equal to Q by V, if you substitute the value of Q, what is V? Q divided by A into epsilon naught into D minus T plus T by K. So this will also becomes Q into A into epsilon naught divided by Q into D minus T plus T by K. This is, or if you go on substituting, that is Q get cancelled. Now C will become A into epsilon naught divided by D minus T plus T by K. This is the answer. This is the capacitance of the parallel plate capacitor. This is the parallel plate capacitor. If this K is, if in the equation, okay, in the equation C is equal to, so I have derived the equation C is equal to A into epsilon naught divided by T minus T plus T by K. If this thickness of the capacitor and K will be the small, then the equation will become capacitance of the parallel plate capacitor. If you introduce a dielectric slab inside the two plate, two metal plates, then the C become the capacitance of the metal plate, that will becomes epsilon naught into A divided by D minus T. This is the expression for effect of introducing a metal plate between the two parallel plates. Okay. So I hope this concept is clear to you. Next, and most important concepts related to your syllabus, that is series combination and parallel combination. So I hope this concept is clear to you. So dear students, today in this session I have discussed the concepts, that is capacitor, capacitance of some simple capacitors, that is maybe in a spherical capacitor, in parallel capacitor, what will be the capacitance of the capacitor, and for cylindrical, and also effect of introducing a metal plate. Okay, effect of introducing a metal plate. So I hope this concept is clear to you. So in next session, let us discuss the series combination, parallel combination, and what are the concepts related to, and further. So let me uh, discuss in the next session. So by today, I'll wind up this session today itself. And don't forget to subscribe our channel, and please learn more and learn the things every day. Don't waste your time. Start preparing for your examination. Thank you. Bye bye.